it's interesting to see how backpropagation is actually implemented in Python code. And for this, we are going to look at a library called Needle, which is a minimal, let's see here, it's a minimal deep learning framework proposed by CMU. And for educational purposes, it resembles PyTorch quite a lot in its interface, and it's perfect for us to see how automatic differentiation is implemented. The two questions we are interested in when looking at this library in this lecture: how does the computation graph gets formed during the forward path? And then how does the backprop algorithm gets implemented? So maybe let me pull up the library here. I have it here in VS Code, this library. Let's first address the question of how does the computation graph gets formed in the forward path. So for instance, if we were to write these tensors A and B and then do a product of this to obtain tensor C. So what's really happening here is that in this case, an object of tensor class is being formed. And in this implementation, this object has a few attributes. Specifically, these are op. Basically, what was the operation which led to the formation of this tensor? What were the inputs? What were the input tensors which the operation acted upon to result in this tensor? Cache data is what is the value of this particular tensor. And requires grad is, do we need to keep track of the gradient of this tensor during the backward path? Here, I did not specify requires grad because by default in this library, it's taken to be true. When we do this, so for instance, e equals to tensor 2.0, this object gets formed and the attributes get populated like this. The op is basically none because there was no operation of which E was the result. We directly formed this tensor by giving it the value. And hence the inputs as well, it's a list of nothing. It's an empty list. The data which A contains is 2.0. And similarly for B, when we do C equals to E star B, the result which we have is another tensor object where op keeps track that there was a multiplication of acting on the inputs A and B, due to which C was formed, and the resulting value of C was 6. This is really the interesting part, which will tell us how does a computation graph gets formed. Now, when we do A times B here, Python doesn't really know what to do in this case because multiplication of tensor objects, it doesn't know how to do that. So really the classes should define what should be the behavior when I am doing E star B. And the way to handle this is by means of operator overloading. So in the tensor class, we have, by means of operator overloading, we are able to call this particular function which has been implemented in this class. So underscore multiplication underscore. And when we're doing this, really what happens is this method of object A gets called along with the parameter, the second tensor passed to it. And now let's look at this particular where this is in the library. So we are looking within the tensor class here, and this is the point where they have defined this. Let's see. Yeah, this is the point where they have defined the overloaded operator. So when we call A times B, really this is the one which gets executed. So again, this method is called for the object A, passing the object B to it. So it's basically the object B. And here, it's calling something else. And the result of this whole thing is the tensor C, which we have shown here. And that is what is being returned here. So we do know that in C, these attributes are populated in this way, in this desired way. Now, how does this get done? Let's look at it a bit more closely. So here, this part is really forming an object of the class operator, which is called e-wise, element-wise multiplication. And this class is defined here in ops.py. Sorry, the previous file which we're looking at was called autograd.py, where automatic differentiation is implemented. In ops.py, we see that there's a class and it has two functions defined on it, compute and gradient. And that's what we see here as well. So we have an object of this class, e-wise element-wise multiplication, and it has these two methods which are contained defined within it. Let's go back again here. So once we have that object, then I am calling that object by passing on these arguments. And I'm able to do this because I have the magic function called implemented somewhere. So I see that there's no magic call here implemented within this class. And we see that it's inheriting from tensor op class. And when we go to this class in autograd.py, there is this magic call defined here. And really, this is basically where the new tensor is being formed. It calls the static method make from operation, where for this new tensor, I am specifying what was the operation. Basically, this object, I'm passing on this object to populate in the new tensor and the inputs as a list. So A and B as a list. So the new tensor gets created here. And here we populate its attributes with op and inputs. This is the point realized cache data where we compute the value of the tensor C. And so because the element-wise multiplication class, it implements compute, we are going to call this at some point when we are doing realized cache data. So let's see what's happening here. And we see that it is calling the compute method of op. So if the compute method of this class gets called with these two sort of arrays. NT array is a generic term. In case of CPU, it could be NumPy array. In case of GPU, it could probably be a CUDA array. And fine, let's go back. So this gets called, and that's how when calling this, we are able to form the tensor C. Let's go back to the point where, yeah, so we were here and we saw that this returns a tensor appropriately populated, keeping track of the operation which generated it, the inputs on which the operator acted, and the final value of the tensor, the final value being contained in the cache data attribute. There are other operator overloadings defined here, not an exhaustive list because it's an educational repository, but the basic functionalities for addition, for division, for something, and so on. So we have an idea of this keeps on. So let's say if you had D as C times D, then a new node would be added here for tensor D, and it would be connected to tensor C and B, and so on. The computational graph will keep on expanding as we define more operations. Then finally, we call backward on the final tensor. So in this example, we call it on C itself. And the backward is really, let's go back here. So the heart of the backpropagation algorithm is really implemented in this function. What backward does is it seeds with 1. Because if you go back again to this example, which we have, so we know that V3 bar is 1. And once we have that, then we can start the backward operation. And that's what backward is doing here. It sets this outgrad to be 1. And then it calls this function which does the computation, implements the backprop algorithm. The data structure which it uses here, it's a dictionary, and this dictionary says that for a particular tensor, what were the contributions coming from its child nodes? So this is what this dictionary is keeping track of. And what we're going to do is, so we started from here, from V3 bar, and this operation, the way we are doing it here, it suggests that there is an ordering in which I should go when doing this computation. And this ordering is precisely the reverse topological sort. So topological sort basically means, so for instance, consider this graph which we have. And if you were to think that to get V1, we had to satisfy dependencies X1 and X2. To get V2, I had to satisfy dependency V1. To obtain V3, I had to satisfy dependencies V2 and V1 and so on. So a topological sort is basically, it gives us the order in which we should satisfy the dependencies so that we have everything needed when we arrive at a node. So for instance, when we arrive at V3, we already have the values of V1 and V2. For the backward pass, we are interested in the reverse of that. So with respect to this graph, a reverse topological sort is, I first deal with adjoint of V3, then I deal with adjoint of V2, and then I deal with adjoint of V1. And the reason for this is, while computing adjoint of V1, I'm going to need both adjoint of V2 as well as adjoint of V3. So it makes sense for me to compute adjoint of V2 before adjoint of V1. And to do this, formally, it ends up being that we consider a reverse topological sort of the graph and go in that order. This is where we do a reverse topological. So basically, we give it the output tensor. And because we saw like the tensor class is such that it links to the inputs which produce this, so we can trace this backward, and then we can look at the graph and obtain its topological sort by here the version which is done. It's a post order depth first search traversal on that. Once we have that, the reverse sorted order of the nodes, we can loop over that list in that order. And for each node in that list, I'm going to sum up the contributions. So recall that this particular dictionary, it suggests what are the contributions to the adjoint value coming from the different children. And we saw from the backprop equation that the adjoint of V1 is basically the contribution coming from here and here. So if I add up the elements of the list corresponding to this particular tensor, that's the adjoint value which we'll get. So that's exactly what we are doing here. We are summing up the elements of the list corresponding to this particular node and setting the grad attribute to this. And then what we need to do is, once we have the adjoint of something, I need to propagate it to the parents in the computation graph. So for instance, once I have V3 bar, then I need to pass out this message in a way to the parents in which are V1 and V2. And this is what I'm exactly doing here. So for all the inputs which generated, so for instance, the inputs V1 and V2 generated V3. And I can look at the inputs, that particular list. And for each of those inputs, I propagate the gradient, which I have the adjoint value, which I have obtained. In fact, it's the adjoint times the local partial derivative. And that computation is happening here. So when we call gradient as tuple, what's really happening is the gradient function of that particular operation is being called. So for instance, our operation in this case it's an instance of element-wise multiplication. And The gradient here given, so out grad is basically the upstream gradient, which we said. So for instance, in this case, V1 bar would be my out grad. And the inputs are here x1 and x2. And the gradient is basically what we saw here. X1 bar is x2 times V1 bar, and that's exactly what we see here. So the first component is V1 bar times x2 RHS. So LHS is basically x1, RHS is x2. And then the second component, which is x2 bar here, that is V1 bar outgrad times x1. So really it's this that I keep on going backward. I compute adjoint of my current node. Once I have that, I pass on this message to the parents by multiplying with the local partial derivative. And once I come to any particular node, I'm sure because of the reverse topological order that I have received the contribution from all the children. All I need to do is sum them up and then pass on to my parents in the computation graph. So yeah, that's all. Yeah, basically like a high level overview of how it gets implemented. If you were to look at a framework like PyTorch, we would see that there's a lot more code because there are a lot of optimizations are happening which are not present here because this is to convey the basic idea. So that's all for today, and thank you. See you in the next lecture.